should be, going through all at the same time, in which case you're limited by the narrowest pipe.
And then yeah,
So it's one.
then it transmits at what? This is a bad implementation, right? It transmits at 7 and or receives at 7 and transmits at 1, right? But in that type of network, 1 is the bottleneck, right, in the chain, so it transmits at 1.
So technically, it's 1 4 times.
It's 1 4 times.
Oh, I got the one part
I
right.
screwed that up.
They're giving partial credit, right?
Yeah, we'll go through, particularly on 32.
I have a question. Like, compared to the 1 gigabyte to megabyte, is equal 1024.
Yeah, 1020.
Yeah.
Or what? Yeah.
You're only
Okay.
able to send. So it's not
So
like it speeds up.
this is a good question, and I will look at all 32s because
Right.
the deal is when we measure network speed, what is our base for network speeds?
Yeah, you kind of ball.
Bits.
Huh?
Bits.
Oh, yeah, it's bits, right? But when I say a megabit per second, what is that? That is 1 million even bits per second,
Yeah.
Right.
right? When I say a gigabyte of data, how much is that?
You have to multiply by 8.
Right? It's yeah. So there is a difference. I will check 32 just to make sure, because
So it will not
I had a question.
I will not deduct for that.
About bits and bytes then. With a gigabyte, are you doing 1024, or are you just like taking the number of bytes, multiplying by the number of bits to get bits?
So, in specifically
Because there's lots of different ways.
yeah,
to
it's specifically in question 32, which is probably going to be the issue here.
Yeah.
It says you're going to do a 1 gigabyte file,
Right.
right, across a 1 megabit link,
Right.
right? So there is the 8 to get from bits to bytes, right?
Okay, so you are taking a gig of bytes, multiplying by 8 to get to bits.
Correct.
Okay, you're not doing like the 1024.
Except for it's 1024. So a gigabyte is 1024 bits, where a megabit per second in network terminology is exactly 1 million bits.
Or we can just
But
convert
I will
from
check.
Giga.
That matches what it says on page 83 in the book.
Yeah.
Correct.
Let me see that.
I will check.
See what it does? It adds up to all the
This section is
Unfortunately, that's just the case, right? So.
I think I forgot the factor of 8 a bunch.
You're okay with typed answers, right?
Huh?
You're okay with typed? Oh, okay.
Mike Grader would really appreciate typed answers, but well. All right.
My brain.
Oh, so we didn't say like.
So the physical layer was the easy part.
Yeah, yeah. Oh.
Easy part's out of the way. And it's really easy because we didn't actually do the electrical engineering part of it, right? So that makes it easier. So we're gonna go up, right? So we did the physical, and now we're gonna go up. And what's above physical?
Data link.
Data link, right? Link. So often the link layer and the physical layer are implemented together. And the reason is because link layer is, if you look at the OSI model, is responsible for framing, right? And framing is the best place to do error correction, right? Because normally you want a blob of data to do your error correction on. There are some stuff that you can do with bits, but it would be better if you did it with some kind of blob of data. So, now we're going to really talk about, but network, right, is going to send some kind of packet down, right, down the stack. And we will talk about that next after we get past the link layer, right? And then it goes to the link layer, which adds some data to it. So some of the things that it adds, particularly in this layer, is it adds a header and a footer or a trailer. I think the book refers to it as a trailer. So it adds that data in there. And this is where we are going to, when we get into it, we're going to actually put some of our error correcting data in there. And then it goes down into the physical. right? And then goes across some wire and works its way up. And it adds it as it goes down, and when it comes back up, back over here, obviously it removes the stuff, right? So the network layer sees nothing of what the link layer does. Typically, so stuff that we will talk on later in the semester, like the application layer, is all implemented in user space. This stuff down here, network, is implemented in OS. The link layer is implemented in OS and hardware. And the physical layer is obviously implemented in hardware. Why would we not implement everything in the link layer in the OS? Or everything in physical layer?
Because of universal requirements for interfacing between systems, universal requirements with hardware interfacing.
Correct, there is universal requirements, but let's say we could go back to the drawing board and we're gonna say, hey, we're Intel and we can control whatever we want, right? So we are gonna go and make the Linux community, the Unix community, and the Windows community, you know, all the companies involved that implement it in one. Why would we not want to do that? Any guesses?
Technology improvements.
Because technology improvements, right? So there are some things that you could do in the physical layer that aren't possible to do in the OS layer, right? So like stepping, layering, right? So when we were talking about, hey, how many signals can we send in the sample size, right? For different signal strengths, that can't be, for obvious reasons, implemented in the OS, right? But you're telling it to do, you're going to send a higher voltage or a higher frequency or whatever in the frequency layer, and maybe that's how we delineate frames, right? That has to be done in the physical layer. However, there are some things that we might want to do in the link layer in the OS, like algorithm improvement, right? Once you put things in hardware, it's very difficult to get it out, right? Because you always have to be backwards compatible, right? And so there is a logical division and a logical reason why the link layer is implemented in both the OS and the hardware layer. But because it's implemented in the hardware layer, this is why the link layer and the physical layer are often implemented together. They decided, hey, this is going to be software, this is going to be hardware, and we'll go ahead and implement these things together, which is where the OSI layers fall apart. So, before we were talking about the physical layer of dealing with signals. Right now we're gonna assume that we have the signaling part somewhat correct. There may still be errors in our signaling, right? And then we're gonna get a stream of signaling data, and we're going to assume the physical layer presents that as bits. And we are going to now have to decide whether that is correct or not. So you get a stream, and that is going to come into a frame. The question is, how do we frame it? What's the easiest way that you could frame it?
Set number of bits.
Set number of bits, right? We do this in files all the time, still, right? I teach this in the C class. Right, we're going to make a complex data file, right? How do you make a complex data file? Well, you usually say, hey, this is the amount of data I am storing here, and then you have the data. And then this is the next amount of data I'm storing, and then you have the data, right? So we're getting a stream of bits, right, that goes on, right? And so we say, hey, first one is 6 bits, right? So then this is data, right? And then since the next 6 bits of data, then here is a number, another one. And let's say this one is 4. Right? And so then it jumps over here. past the 4 bits, and then, you know, this is 7, and so on and so forth, right? And so now we have framing, right? We can actually say, hey, we have a delineated frame. What's the problem with this? There's a giant problem with this. Huh? No, well, I can do 100 bits, 1,000 bits, right? It's actually it's very little overhead, right?
You lose track. Synchronization.
Well, synchronization. What happens if you lose track?
Throw it all out.
Like, let's say, for whatever reason, remember we said it's not perfect, right? Let's say that this was supposed to be 6, right? But a bit got flipped, and since it was supposed to be 6, let's say it was the 4-bit, right? Now it's 2, right? It will go on and say, oh, next 2 bytes are all right, and then now we're at 4, right? And so we can get rapidly out of sync. And there's no way for you to tell when this simple method, how to resync. What is the only method that you can do to resync this? No, you can't, because you're resending the data, you're just sending more streams.
Close the connection and
Find
reset.
out.
You have to shut down the entire connection and start over. Probably, since shutting down the connection is also sending data, you have to hard reset the entire system. You have to turn the internet off and let it come back up to resync. That might be a problem, right? Or at least you have to do, you know, some segment of the network, who you're talking, whatever. So if you had 2 big internet pipes connected to each other over SONET or something, and is shooting data, you have to turn the thing off, let it reboot, come back up to be in sync, and the next time you're out of sync again, you have to turn it off again.
Is this actually used anywhere?
No,
Oh.
no. This is why this was a naive example, right? Oh, but we do this in files. Why do we do this in files and we don't do it in the internet?
It's reliability.
Yeah, high reliability and stuff.
Well, there is high reliability of files, but if you get out of sync in a file, you can simply close the file, reopen it. There's not a big system that you need to redo, right? Or you don't even have to really close the file. You can just go back to the beginning of the file. This is a string. You can't go back to the beginning, right? So, bad way to do it, right? Even though we still do it in files. And most files are implemented that way, in some form of that. It gets much more complex, and you get linked lists and pointers here and there, and relative pointers and hard offsets and stuff. But files are still implemented that way. There's another way to implement files. This is actually a non-preferred method to implement files. Is how else would you delineate data inside a file? How would you do that? So instead of having a number and some data, and a number and some data, and a number and some data, there's another way to do it.
You talking about like a protocol, like a preset standard?
Yeah,
data
so
block sizes?
it's called in files, it's called a sentinel character, right? If I write this character, it means the end of my data and the beginning of the next data. And when you're doing that in files, often it's like, okay, if I'm doing a binary file, and I can have a range of 0 to 255, then my sentinel character can also be in my data. So how do I distinguish that? And there are various methods of doing that. But one of the methods is you can escape it, right? So if my sentinel character is X, then if it's in my data, if it's in my header, right, that's the start of data. If it's in my data, we need to escape it. So we can do that however, right? If it's in my trailer, then you don't escape it, whatever, right? Some way to frame it. Now, if we're going to frame it, there are a lot of other ways that we can do this, right? We can simply write X twice. So normally in files, that's how you do a sentinel character, is if your sentinel character is X, you always write it twice if you need to escape it. If it's ever found by itself, then it's a sentinel character. If it's not found by itself, it's found in pairs, then it's not. And that, as odd as that sounds, it will always work, right? If they're always found in pairs. So if if the data is X and it's inside here, right, I can simply write XX. Well, what if the data was XX? I simply write XXXX. Right? What if the X was like right here, and then I had this?
Triple X.
Huh? Well, so it would be XXXX because this is inside the data, and then another X. Right? Now we have an odd number, and we can distinguish that. It's not the best way to do it, but it is a way to do it, and it always works. Another way we could do it, and this is called byte stuffing, by the way. If we want to byte stuff, we can use an escape and some kind of flag, whatever that is. So instead of writing that, I'm just going to escape, right? And instead of writing flag every single time, I'm going to write X. It's really not the character you would use, right? But so we're going to do this parent. So if we have an escape X, then that is data. And if it's not escaped, then it is a flag, right, for our header. The problem with this is now I can have escapes in my data also, right? So now, if there's an escape in my data, I need to escape it, right? If there's a flag in my data, I need to escape it, right? And if there's a flag in the header, right, which is usually there, right, the first thing, then it doesn't get escaped. How do we make this better? And by the way, this is actually how it's implemented, or at least we're getting close to it. How do we make this better? Any ideas? So right now, we have some problems, right? So escape needs to be escaped as what? Double escape. And a flag needs to be escaped as escape flag. Now, what about these?
Escape flag.
Yeah, escape, 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 flag, right? And escape, 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 escape. If that happens to be in the data. So normally when you choose these sentinel characters, by the way, you do a data analysis and you see what shows up. Rarely. Most prolific number in all data is 0, so you wouldn't want to pick that. Right? So we can make this better. And we can make it better by making sure that inside of the data, a flag can never occur.
Oh, so you just substitute.
Yeah, so we can substitute. But how do we know when to substitute?
Overhead.
So it's not as much as you think, because we're going to be tricky about our substitution, right?
You just hit it all up against something.
Huh?
Could you just hit it all up against something, so it just all processes through?
Yeah, well, we're just going to do math on the next character. We're going to do actually a one cycle math on the next character. So there are things inside of a CPU that are very fast.
Every flop basically.
Yeah, and one of those is Zoring, right? If you XOR something, it can be done in almost all CPUs in one clock, right? Your CPU is running at 1 billion something clocks, right? So taking 1/1000th of a second to do this is not that much of an overhead. So what we do is we say, hey, and I think the specific, and I'm using these numbers because it's actually implemented, I believe in Sonnet, is our flag is going to be hex 7E, and our escape is going to be 7D. So that means that every time we see the byte 7E, we want it to be always in the header, right? Always a mark of a frame and never in the data. So what we do is we escape it like we did before, where this escape 7X, right? We XOR it with 20. Well, when we XOR it with 20, 20, right? 20 is right? We're flipping one bit in there. So if we take 7E and we flip it, that becomes 5E. And then we say every time that we see an escape inside of our data, we flip it we XOR it with 20 and flip that one single bit.
So it's always XOR with the 20?
Huh?
We always XOR with the 20?
Always XOR with the 20. Right? Which basically turns off the bit in the 7.
That's just the ASCII character table value for the escape.
Yeah, but you don't care at this point, right? It's just raw data. You don't care what ASCII values it is. It simply translates the raw data. And so then if we do it this way, that means that our escape also needs to be XORed, right? Because every time we see an escape, we need to XOR it, right? So that becomes 5D. And that time, every time you see a 7D in the data, it is time to do a XOR with 20. Right, and so when you encode it, you do the same thing, and one of the properties of XOR is that to undo it, you simply do it again. And it turns the bit back on. Good.
Sorry, this may be a simple misunderstanding, but I'm confused. What characters do we actually use as the sentinel, or the escape? In the
So 7E is a non-printable character.
What? Sorry.
7E is a non-printable character. It's
So it's
well
not
out of the ASCII range.
Okay. Okay, so those are the actual values.
Yeah,
the
so these are the
those
actual
hex
values,
in the-
right, hex
in the bit
values.
value that
Yeah,
we actually-
obviously, we're getting a stream of bits,
Mhm.
right? And the bits are interpreted, we're using hexadecimal because it's way easier than putting a big line of bits
Right,
out.
got it. That's what I was
But,
thinking.
yeah,
Just-
it's simply, and we already have some big line of bits stuff to do today because we're gonna do polynomial math, and it's gonna be a giant, long division that we're gonna do, right? But maybe, we might not make it that far, I don't know. But we just normally just do things in hacks. But
So
it's
but
coming
that's the
across.
standard value
Yeah.
that's used. Okay.
And so this is the actual, so actually there's more stuff over here. And we're gonna talk about that somewhat. So this is actually point-to-point protocol for those guys that have been around a while. You used to be able to get internet at your house with point-to-point protocol, right? But it's still used inside the internet for sonic connections. So these multi-gigabyte pipes that are going in the core of the internet still use point-to-point. And so it has a header and a trailer. And then there's data, I think here. And then there's some control information, and then a checksum that we put in there. Why would we need a control field?
Do you know which frames that's going to work, maybe?
So possibly. So remember, we're pulling it down from the network layer, right? And we receive a packet. Does that packet? Do we guarantee that packet always goes through the same pipe?
Depends which one.
Yeah. So it might not. And so there's particularly in point-to-point protocol, it might go through multiple pipes, right? And so you need now some information on how to reassemble your fragmented packet, right? To pass it back up to the network layer. So, and then we need a checksum, which looks like D sum, but it's
is that the ability for it to fan out multiple pipes, is
Correct.
that dependent on the protocol that's being established?
Yes, it would have to be built into the protocol.
Okay.
So this is just point-to-point protocol. And I do that because, you know, normally we say that we add a header and a trailer,
Mhm.
right?
Right.
But there's reasons that we have information in there. And when we say, in the network layer, there's almost always a trailer, and it's because we need to stuff other information there. Namely, how to do checksums and stuff that we're talking about today. It's gotta be placed somewhere. And preferably won't be inside of the data bank. Go ahead.
What is that last thing in the far right?
A trailer.
Ah,
TRL.
trailer, okay.
Yeah. Trailer. And it's often, when you're doing files, right, it's called a footer, not a trailer, but it's the same idea, right? All right. So now we got framing. So now we can frame the packet, or we can delineate the frame that it encapsulates our packet. Now the question is, how do we deal with errors? There are, let's take a look. Remember when I was, our things that I've been drawing here, right? And you know, that means that, you know, in an ideal non-analog world, right, or digital world, it looks like this. Anything above the lines of 1, there's some timing. We talked about this, right? But when things really come over, they come over with noise. And that's not bad, but as the line gets longer, right, the signal gets attenuated, which means that the things that we're sending get smaller, right? So it starts to look like and then you have this line that you're trying to measure. And eventually the noise will start overcoming the attenuation, right? And you'll start getting error bits. This is why we have errors in our physical layer, right? Because as the line gets longer, our signal gets weaker, but the noise doesn't get weaker. It's still there. So we get errors in there. And we talked about various ways that you can handle that in the physical layer, but it's never going to be perfect, right? So over optical fiber, it's way better. That's why we can go these long distances. Over copper, it gets way worse, right? Especially bare copper. So there are two methods to deal with this. One is we can detect, and then of course we'll have to retransmit it if we detect. And then we can also correct. If we send extra information, we might be able to correct. And then if we can't correct, because it's, for whatever reason, it's really messed up, then we can ask for a retransmission then, right? But basically, it's detection and then correction. So how do you add detection? Another naive example.
Parity bit or checksum or something.
So we can do a parity bit,
Well, it's not very reliable.
right? We can do checksum. What else can we do?
CRC?
CRC. This is our long division problem later. What else?
The acknowledgements, based on the acknowledgement number, we know which one the access number.
So, yeah, but acknowledgements, remember, that is handled in transport, right? So and there is error correction in transport because we're actually gonna do all of this work here and then I'm gonna tell you, and sometimes errors get through, right? So then we have in the transport layer, if you could do acknowledgement that it's been received, because some things, we can do all the error correction in the world, then what happens if the packet doesn't arrive, right? So you can do all the error correction in the world. If the packet doesn't arrive, you can't correct that, right? And you can't, the network and link layer, the link layer, not the network layer, doesn't know that the packet, there's no way for it to know the packet hasn't arrived, right? So we'll deal with that later. But it is a way of doing error correction, so you're not incorrect. Just we haven't got to that level yet. So let's start out with something super naive. Let's just send the data twice, right? If we have something, relatively low amount of errors, right? We send the data twice. If it's the same, sure, right? So let's see. We're going to talk about code words, right? We are going to build into our data code words. So for this very naive example, we only have 2 code words, and that is 0, 0, 0, and 1, 1, 1. These are our only code words. And so every time we need to send a bit of data across, right? Zeros are represented by 0, 0, 0. 1 is represented by 1, 1, 1. Now let's take an analysis of this. 1, we have to submit 2 times the size of the data, always, right? Because we're sending simply a duplicate, right? But what are the errors that we could have? Yeah, let's just change 1 bit. So these are our code words. I'll leave them up there. Let's say I send 0, 0, 0, right? 0, 0, 0, double our data, right? And it goes through the pipe, and it comes out 0, 0, 0, 0, 0, 1. So we could definitely detect that there's an error, right? And we can ask for a retransmission. Right?
But, sorry, excuse me. In this case, is he looking at it from an odd number perspective, or it's looking at it from a fixed tree number unit, like 0, 0, 0?
Yeah, let's say we built in the framing, right? We've built in the framing. So we definitely, we know we have the framing correct, right? So we're just moving in of our thing that we were doing before, right? We're only looking inside of data. And let's say we're not doing checksums or anything else outside of our data. So we're just going to build error detection and error correction inside the data stream itself. So how many errors can we detect in this? So we can detect up to 2 errors or 3 errors, right? So if we send it twice, right, we can have 0, 0, 0, and then, you know, if it's really bad connection, it arrives as 1, 1, 1. Right, so that's 3 errors that we can detect, right? But that's not the best question, the error detection, is really how many bits does it take to fail? We're not doing correction yet. We're just, how many, in the error detection with this scheme, how many detections does it take to fail? And that answer is 1. If we get 1 bit out of 6 bits, by the way, that we have to transmit, then this method fails. So it turns out that sending duplicate data is not a great way of doing it. It has a lot of overhead, and it only can it fails on the first thing, right?
Why does it fail? I'm sorry, on the first one.
So for just detection.
Okay.
So it fails because we're simply saying, does this equal that?
Got it. All right.
If it doesn't, retransmit. But if we're sending these code words, right, if we end up with 001 over here, it's very likely that this was actually 000. Right, so we could write a correction scheme that says, hey, if you get these invalid code words that are 1 bit off from being valid, then simply correct it. That makes sense, right? So we simply correct, if we get 0, 0, 1, we correct it to 0, 0, 0.
How does the receiver know this is going to be 0 or 1?
Because the physical layer passes up, says this is 1. Now, in real world implementations, the physical layer might pass up to the link layer a vote of confidence. This was a very strong value of 1. This was a very weak value of 1, right? And so there are other, because the physical layer is analog, so you can have large and small values of 1, right? Strong and weak values of 1. You can have strong and weak values of 0, right? Because you're pulling that out of an analog signal. In reality, the physical layer does in fact do that. But in this particular case, right, let's say that the physical layer passed up 1. We don't know that the 1 was really shallow or really strong, nothing, right? So we just have to accept it as 1. So we can still do error correction with this by saying, hey, if we know the probability of flipping 1 bit is much less than the probability of flipping 2, right? Especially, you know. And so we can implement that scheme, and then things that are close to 0 get implemented or get translated to 0, and things that are close to 1 get translated as 1. That's pretty straightforward, right? So some of the properties of this still aren't all that good in this error correction scheme. One is this might work well for random errors. So you get an error occasionally in a random dispersal pattern across your data, right? So if your error was 1 in 100, the odds of them being right next to each other pretty small, right? Unfortunately, a lot of mediums have bursty errors. So what happens if the errors are very bursty? Right, so that it is very likely that you get some 100 repetitions of 1 or 100 repetitions of 0, right? Because there's some signal or something overlaying the line that simply kills it or amplifies something. Well, now this error correction scheme doesn't work at all, right? So if you got 100 repetitions of 0, it's going to say correct, 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 correct. Right, on down the line until the burst of errors is over. But it does work pretty well for random errors, other than being horrendous on you're consuming all your bandwidth because you're having to translate the data twice. But you can correct it. So I want to mention right now is all of this stuff that we're doing for accidental errors, things that occur naturally in our network, not malicious errors. Malicious errors are something different. So, the next one that we can do is we can do parity. Right up there. What's parity?
Making the sum of the ones odd or even.
Correct.
Adding another bit.
So if you want like the formal definition of parity, right, is the binary sum modulo 2, right? So, which is the same as a XOR. So you simply go through and you start adding them all together and then modulo 2. So it turns out that it's just really just counting odds and evens. If there's an odd number of ones, the parity is 1. If there's an even number of ones, the parity is 0. So in our 7-byte code word right here, there's an odd number of ones, so the parity is 1. And that makes 1 byte, right? That on the receiving end, you simply have to make sure that everything XORs to 0.
And that's just for even parity, right?
Yeah, so if
typically use more than odd parity, or?
So set 7 bytes again. Oh, I already put 3 in there. And we do 4 ones this time. It's 1 plus 1, which modulo 2 is 0, plus 1, which is 1, plus 1 is 0, right? So we had a 0. Because in modulo arithmetic, right, it simply just alternates back and forth.
Wait. So, explain that again. You have 7 on the top line and you have parity 1.
Yeah, so this is the parity bit right here, and this is the parity bit.
Okay, gotcha.
But, I mean, isn't there, but there's 2 types of, there's an even parity, which is what you're describing right here, and there's odd parity, right, where it's like it adds, and that adds a 1 on the end if it wants to make it odd.
Correct.
So,
yeah.
Since you went straight to even, and you kind of didn't mention the odd one, is the even parity like what's kind of the industry standard, or?
Yeah, so we're just progressing. I can tell you that we're not doing to implement this at all, because we're going to take an analysis of this and we're going to see this might be worse than the last one,
Okay.
right? Right. So so let's just jump right into the analysis of this, right? We can do parity, right? So we can have bigger code words and we have much less overhead. We're only transmitting 1 extra bit for every 7 bits in this case. But how many errors does it detect?
1.
Huh? Again, our detect is 1. What happens if there's 2 errors? Then it doesn't detect at all. Right? It completely fails at 2, right? So we can detect an error, right? But at 2 errors, we think we're right. Right? So it's worse than our last code word. Right? So weirdly enough, one of the strengths of parity is that it can detect odd number of errors. Doesn't really help us because really we're kind of concerned about that number 2. Right? But it can detect odd number of errors. So this doesn't work out too well either. So let's take a look at a checksum. It's on our list up there, right? Checksum. Checksum is actually implemented in the IP layer for network. And I believe it's also implemented in TCP and UDP. Right? So it's already been implemented, so it must be good, right? Right? So,
Just like our governmental
so now we have a checksum. We're not going to encode our data with parity. We're not going to encode it with double code values or anything like that. What we're going to do is we're going to take advantage of the trailer and we're going to put in a value there. So now we have data in here, and I believe in the book it refers to check bits as R. So the check bits, we have we have data, which is the number of bits is represented by D, and then we have some checksum where the number of bits is represented by R. That checksum could be 1, which is essentially parity, or it can be something larger. So now the checksum to bring, who in here has had cryptography already? Right, to bring back some really bad memories of cryptography, right? So the checksum, an ideal checksum is a randomized distribution inside of a field representing the data as a whole, right? So the idea is a checksum is fully randomized, so it is some perfect fraction of a field, and it doesn't repeat, right? But the data going in is larger, right? So by necessity, because the data is larger, I just told you it didn't repeat, right? But the data is larger, so there will be some input values where the checksum is obviously repeated because there are more numbers going in than there are coming out. Otherwise, we're right back to our problem with sending double the data, right? We could have a checksum that is the same size of the data. We could have a checksum actually that's larger in the data and really waste some time, right? But the idea is we get a randomized distribution, right? This is the idea of a message digest. And that size of that distribution gives us a probability of a data code word being repeated inside it being very small, very small. So we have D in here, and which is data R, right? But we can take it as a whole because there's really no physical block, right? It's just a stream of bits, and we can say that it can be represented as D by R, and R is a function of D. Where this is a randomized distribution. Right? It doesn't repeat things often.
So, by randomized distribution, are we talking about a pseudo-random number?
No. So it is a randomized distribution. So the easiest way of taking a randomized distribution, the easiest way to think about that, is take a prime number and use it as modulo. Right? So if I put D, and this is not what checksum is because you want it to be more random because this pattern repeats, right? But there would be a way of this repeats 0 to 6 over and over again, right? No matter how big D is, this always repeats 0, if we're progressing linearly, then it repeats 0 to 6, right? But I could do things to this, if we go back to our encryption class, right, to make that much, much more random, right? So I put some shifts in there, and I modulo again, and over again, right? And I start getting this fully randomized distribution, right? That the input D, after I start doing shifts back and forth and modulo or prime number, then the linear sequence D is randomized on the other side. It's no longer linear. Right, so it's a randomized distribution. So, and the reason you want that is because it has some great properties in cryptography, but it also has some great properties in error correction for some of the same reasons. Right? So we have this big, giant field of possibilities of code words that are represented by 2 to the D plus R. Right? So if we make R decently sized and D is decently sized, we have this giant, vast set, right? So, and this is 2 to the D plus R because this is really a stream of data, right? So we can have 1 or 0, and this is just a binary stream of data. And how much data is inside of this field is represented by a D, or 2 to the D plus R. Now, inside of here, we have D, which is represented by 2 to the D. So if we make R some decent size, right, the probability that a random piece of data, an errored piece of data, is inside of this code word becomes 2D over 2D plus R equals the probability. And what does that reduce to? 1 over 2 to the R. So it's 1 over 2 to the R becomes our probability that a code word that represents the data and the checksum at the end is accidentally made. And you can notice that if R is somewhat decently sized, like 16 bits, right, the probability is really small. Because that's in bits, not bytes, right? So if R is 16 bits, you know, 2 whole bytes, then the probability that you have an accidental collision becomes extremely small.
I think
Hmm?
that's supposed to be 2 to the R, not 1/2 to the R. Because if we break it down, it becomes 2 to the power of D minus R. Actually 2 to the power of minus R, if I'm not mistaken. Because it's divided, right? So it becomes negative.
The 2 to the D's cancel out.
Yeah.
2 to the D
The bottom
cancels
is
out.
2 to the D times 2 to the R.
Yeah, and then 2 to the D, so it's like that.
Yeah, so this right here is 2 to the D times 2 to the R, right? And then 2 D's up here. They cancel out, so this becomes 1.
So the checksum, sorry, I should know some of this, the idea behind the probability, it's almost like the idea behind the probability of preventing a collision in a hash, basically.
Correct,
It's like
correct.
the exact same
It
probability.
is the exact same
probability
thing.
game.
Except for,
But this time the
checksums
data-
aren't cryptographically secure, like a
Right.
hash
Right.
digest is. In that, one of the properties that we're ignoring here is like if I have X number of bits of a hash, then I can figure out the following bits of a hash,
Right, right,
right?
the rainbows.
So, yeah, we're not doing that. That's why this is not, a checksum is not a secure hash, right? Because it doesn't have the same property of being able to not predict what future bits are. But,
So basically, the value here though is uniqueness and the probability.
yes,
perspective.
it's uniqueness in the probability perspective, ignoring the ability to guess the rest, right? So when we say uniqueness in the probability is that it is a randomized distribution across this field.
Right.
So this is the probability that an error would look like a code word. Or
So this is the probability of a data and code word pair matching. So we've done parity and checksums. And checksums actually are used in IP.
I have a question.
Uh-huh.
What's the difference between the checksum and the code word code word?
So the code word is the data and the checksum together.
The data and the checksum
Yeah.
together is code word?
Is the code word, right? When we say we have a field of invalid code words and somewhere inside of there is a small portion of valid code words. That is the data and the checksum put together in this instance. But it could also be the data and parity in the previous instance, and or we could have a table of code words like the last one. All right. Now, before we get to our long division problem in CRC, I want to talk about Hamming distance. So Hamming distance, if you guys remember the cryptography class, is the number of bits required to change to make one valid code word another valid code word. So if we go back to our very early double example, right, we had two valid code words. What's the Hamming distance between these code words?
3.
3, right? It is because in order to change one code word into another code word, I have to fit all 3 bits in this thing. So Hamming, when he was writing about this very foundational topic, came up with some neat observations about distances between them. One, he postulated that if there is a code word of an arbitrary size of D plus 1, it can detect up to D errors.
Say that again, sorry.
So if there is a code word of distance, or a code word of two code words of distance, blah, whatever that is, we'll just call it D. In this case, it's 3. Then it can detect up to 1 error. And that is detect. He also said, and we can tell, right, that in this one, we have a distance of 3, right? So how many errors can we detect?
1.
It would be 3 plus 1, right?
So we can detect, let's see. It should have came across 0, but it came across 1, 1. Right, we can detect 2. We can detect 2 errors. And that's because our distance here is 3 plus 1. And I messed that up.
I think about if you can detect D
Yeah.
plus 1, if your distance is D plus 1,
Correct.
then
So
it's actually
we can detect 2, and that equals a Hamming distance. So this is 3. 2 plus 1 equals 3.
What is 2?
2 is the number of errors we can detect. 3 is the Hamming distance. Right? And then this is his formula for detection. Seems really simple. He also said that the Hamming distance is also the number of errors, also determines the number of errors up to, because we've already shown you examples of things that don't, right? But it can detect, correct up to errors with this formula. So Hamming distance again is 3, right? And so then you get 2D equals 2, and so it can correct 1 error in our little code. This is the ceiling. This is just like Nyquist and Shannon saying, hey, if you did this correctly, this is what you can do.
For that formula, error detection equal 1 plus the Hamming distance?
So so this formula here,
No, the one on the left.
okay, this formula here is for detection. This one's for correction. This is the amount of data that you have to send in order to do these two things, and that is the ceiling. Nothing, it can't be any better than that. So let's take a look at take a look at that in actual implementation. In that very same paper, he came up with a scheme to do error correction that is optimal. Now, it's not necessarily an implementation optimal, because ideally you would like the error correction to be in some kind of other separate block that you can process, right? So this goes back to like stuffing it all into the data section. but is it possible, what is a way that we could actually error correct with some kind of efficiency? And so what he said was,
Is there a different marker you can use?
this is probably worse. No, that third way. So let's visualize what our code words are actually doing here, and what we say when we have so if we have a field of code words and we have valid code words, right? The what we're saying is if an error, like let's say that our hit is here, what code word does that belong to?
One.
Huh? It belongs to this one, right? Whatever. I should have put numbers in there. So 1, 2, 3, 4. It belongs to 4. Whatever that code word happens to be. Right? Because it's in proximity where you say, hey, it is closest to 4, therefore it's 4. Now, this means that the number of errors, if I put it here, right, it belongs there.
Is this a stream of data? I'm trying to understand. the
So
table.
I'm just visualizing what we're saying by a Hamming distance, on how far something is away from something else, right? So in this particular matrix, right, if we have basically 4 matrices of 9 different blocks. If it's the closest one, it's the one that wins, right? In this, nothing can be here, right, in between the blocks. So it either belongs to this or it doesn't. So the number of, the Hamming distance to get to one valid code word to another is what? 3. Takes 3 moves to get to another code word. Right, and since the Hamming distance is 3, this is a visual representation of our code words that we've been using here, which are 0, 0, 0, and 1. So this is why we can only correct for 1 error, and we can detect 2 errors. Because if the valid word was sent was 4, and we moved 2, we can still detect, but we can no longer correct because it pushes us into the next quadrant. So, is there some other way that we could make that matrix where it is more efficient? And it turns out there is. We have 7 bits in a row. 7 bits can encode and fully error correct a 4-byte code word. How do we go about doing that? So if you really want to figure out the proof of why that is, you can go read Hamming's really old paper, but it's really actually kind of neat because he does it in a pretty elegant way. But let's say we have a code word of 1011 that we want to send. This is our data. And we need to put this into a code word that is fully error correctable. Hamming proved that we can, anything that is a natural, what do you call that? Natural factor of 2, that you simply leave blank. So 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4. Right? This leaves us 4 open spaces to put data, which is 1, 0, 1, 1. Now what we do is any of these places that have one of the code words in it, we do a XOR or parity.
So will you go over that again?
So if we have 7 bits, right? There, bit 1 is represented by 2 to the 0, right? Because it's 1. 2 to the first is 2. 2 to the second is 4, right? But that also represents in a 3-byte parity, right? Actually, number of bits, right? This is 2 to the 0. This is 2 to the first and 2 to the second. So we go and we look at each of these and we try to determine which one of these bits is actually turned on in that number. So for 3, it is turned on, right? Which one of these 2's is represented in 3? Why? So people are looking at me like, ah.
That's me.
Huh? How do I write out 3 in binary?
0, 1, 1.
It's 0, 1, 1, right?
Yeah. All right.
So 2 to the 0 is turned on. 2 to the first is turned on. 2 to the second is turned off. Right? What is the, so are we gathering?
Yeah.
Is it recording here?
So parity bit, huh?
I need that stuff again.
He just verified it was still recording.
So, yes, yes. So it turns out that for the first parity bit, we parity for 1, which is actually the first bit, but we're just going to place 0 in there for right now. If it's blank, it's 0. And we need to do this because we need to decode it later. So we want the same algorithm. So we say, hey, if it's blank, we treat it as 0 because blank things are usually nothing, right? So so parity 1, parity 2, and parity 4. Parity 1 are which bits? 1, 3, 5, and 7, right? Because it's 1, so it's all the odd numbers. And parity 2 is what? 2, 3. Not 4, right? Because
5, 6, 7.
6 and 7, not 5. Right? And parity 4? Does everybody get why we get this? Okay. So don't feel bad. When I took the class a long time ago, I had to go reread it like 3 times before I figured out, oh, this just simply represents a number in binary, and figure out which ones are turned on, right? So in order to create the numbers 1, 3, 5, and 7, right? Let's do it like this. 1, 3, 5, and 7 are created with some combination of 0 and 1 and always ending in 1. That is that parity bit because it's 1. Go ahead.
Just a recognition, it might help to write P1 above the first column and P2 so that we understand what bits we're talking about are becoming the parity bits.
And then just writing all the numbers, at least first 4 digits. 0, 0, 0, 0, 0, 0, 0, 0.
Okay. All right. So parity 1 is 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, and 1, 1, 1. Right?
Yep.
So that is 1, 3, 5, and 7. Parity 2 is what? So this the middle bit turned on, right?
0, 1, 0.
So it's 0, 1, 1, 0, 0, 0, and 1, 1, right? So did I do that in the right order?
No, close enough.
Close enough. Right? Should have been there, whatever. Dang it.
Yep.
And then 1,
1, 1, 0, 1, 1.
There you go. So the middle bit is turned on, right? Which is 2, 3, 6, and 7. Now I get this little tiny space to do. Parity 3 is the first bit turned on.
I mean, parity 4, right?
Or parity 4, sorry. Parity 4 is the first bit turned on. So that is what?
1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1.
Right, which is 4, 5, 6, and 7. Now, you want to see the magic. So now we've maybe figured this part out. Let's look at the magic of this. So, we have to figure out, for number 3, right? We have 3, 5, 6, and 7. And so for parity 1, we have which ones of 3, 5, 6, and or 3, 6, and 7 are turned on?
All 3. Or no, 2.
5, yeah, 5 is 2. It's
3 and 7.
3,
5 is turned
5
on.
is turned off.
Yeah, so 3 and 7.
7. So it's just 3 and 7.
And then we got explosion.
So this is 1 Zord with 1, which is
0.
0. Right? What's the next one?
Seven. 3, 6, and 7.
1.
So it's 3, 6, and 7, right? It's all 3 of them are turned on. And what is 4?
0 and 1, I'm lost in there.
Huh? Uh-oh.
0.
Uh-oh. Hold on.
Yeah, can we correct?
So let's just go through. I'm going to circle them, and then we'll just erase the circles. Right? So we don't really need to pay attention to this because these are always going to be 0 while we're encoding. So it's really these last 3 numbers, 3, 5, and 7. So 3, position 3, 5, and 7.
Okay.
All those numbers Zord together. So 1, Zord with 0, Zord with 1 is 0. Right? Because we just count the number of ones. If it's even, it's 0. Right? And now, we're going to circle different numbers because we are now. All right, so I'm finally getting around to creating this video because the camera died in class. So I apologize to the people that are relying on the videos. But hopefully this will get you caught up, and I'll get to the next video as well. So what we're looking at is Hamming codes. And in Hamming codes, we're going to encode every 4-digit binary representation of a number in 7 bits rather than 4. So we have 7 bits. That means that we have 1, 2, 3, 4, 5, 6, 7. And the positions for these are 1st, 2nd, 3rd, 4th, 5th, 6th, and 7th. And also notice that some of these numbers are a direct power of 2. So this is 2 to the 0, this is 2 to the 1st, this is 2 to the 2nd. And this, these will be our check bits. And it's important that we actually pick not necessarily the positions, but in normal Hamming codes, these numbers have significance, and it's the reason that the thing works. So if we're going to code 1011, like in the example, right, we're going to put these in the things that are not direct powers of 2. So 1011. Now, for this check bit here, which is 2 to the 0, we are going to look for every binary representation of these positions, which is 2 to the 1st, right? So we're going to include itself for right now, but when we're going to do this for the error checking later, but right now, if the space is blank, we're going to count that as a 0. It doesn't exist. Well, to the 0, so the number 1 in the binary representation is every odd number, right? So it's 1, 3, 5, and 7, and that's because the binary representation of all of these numbers is something like question mark, question mark. We don't. Those are 1s or 0s, and then 1. And then the next one, we're going to look at to the 1st, which is 2. And we're going to look at everything that actually has a 2 in it. So, so this would be a question mark, followed by 1 with a question mark, right? Where the question marks can be 1 or 0s. And I'll put that here. Question. Sorry about that. A question mark is equal to 1 or 0. Okay. Not that you can really read that, but hopefully you're listening. And so in those numbers, right, that is going to be itself 2. But it's also going to be 3. And it's going to be 6 and 7. Now let's do the same thing for 2 squared, right, which is the binary representation for that for the number 4 is 1, and then question mark, right? And so what things have the 1 bit flipped on in the 4 position, and that is 4, 5, 6, and 7. So what we do now is we're going to go through and calculate the Hamming codes that we're going to put in these positions. And we're going to do that simply by taking the sum modulo 2, which we've talked about in class before, which is really an XOR. So you can simply count the number of 1s, and if it's odd, then the answer is 1. If it's even, the answer is 0, including 0 being an even number. So let's go through and take a look at it. So let's start with position here, which is 2 to the 0. Right, so this position is this set of numbers right here. And I'll go ahead and I'll do like some kind of label here. So 2 to the 0, 2 to the 1, and 2 squared, right? So let's take a look at 2 to 0. Well, 2 to 0 represents 1, 3, 5, and 7. So 1 is blank, so we'll count that as 0. 3 is a 1. 5 is a 0, and 7 is a 1, right? So we have 2 1s and 2 0s, so that is an even number of 1s, and we will write 0. For the same thing is on the 2 to the 1st position, the number 2. Number 2 binary form is represented as 2, 3, 6, and 7. Right, so 2 is a 0, 3 is a 1, 6 is a 1, and 7 is a 1. We have an odd number of 1s, so that becomes 1. And then for number 4, we have 4, 5, 6, and 7. And so 4 is a 0, 5 is 0, 6 is a 1, 7 is a 1. That is an even number, so we represent that as 0. So now let's go through and do an error check on this. So we'll just leave everything in the position as it is because we're going to go through an error check. And when we error check, what we want to see is that we always get an even number of ones. So we check to the 0. This time to the 0 actually has a position. It's not blank and it's 0. So we check 0, 1, 5, and 7. It has an even number of ones, and thus there's a 0, right? And so then we check 2 to the first, which is 2, 3, 6, and 7. So 2, 3, 6, and 7, which are all ones, right? So there's 4 ones, and so we get a 0 there. And maybe more appropriately, I'm going to put it in front because we're going to get to the errors here in a minute. And so I put that in front because this is the to the first position, and this is to the 0th position, and this is to the 2nd position. So what is this number? So we check to the 2nd. It becomes 4, 5, 6, and 7. There's 2 again and a 0. So if we have 0, 0, 0, that means there is no errors. Notice that there is no position 0 here, right? So let's go through and change something. And this is the important thing that we stayed after class for the people that are there. Let's change this thing to 0. We have an error here, right? And this, I'm going to put an error. So let's go through and recalculate in the 6th position. So the 6th position is 1, 3, 5, and 7. Or the 0th position is 1, 3, 5, and 7. So 6 is not in there. So we just use our previous calculation of 0. But obviously, in a real situation, we would go through and have to calculate that. And I guess we can do that, right? So it's 0, 1, 0, 1. Even numbers of zeros is 0. So this is the to the first or 0th position, to the first, to the 2nd, right? In binary form, right? So this is the order we put those in. And so now let's look at 2, 3, 6, and 7. So 2, 3, 6, and 7 is 1, 3, 0, and 1. We have an odd number of a 1, so that's 1. And let's look at to the 2nd position. To the 2nd position is 4, 5, 6, and 7. And so we have 0, 0, 0, 1. Now the significance of this is, what is the binary representation? What does that number actually represent? Well, that is to the 2nd is 4, plus to the first, which is 2, plus to the 2nd. And obviously there's either a 1 times this in front here, a 1 times this, and a 0 times 1, right? So this is 4 plus 2 equals 6. This is where our error is, and that is the magic of Hamming codes.